So we will look at the shallow water equation today and higher order finite difference schemes in order to solve that. So for the shallow water equation, let me quickly show you some motivational slides. So let's see, can you see these slides? Okay. So shallow water equation is used for tsunamis, to propagate tsunamis, but not only. So let's quickly look at, for us, it's about computing tsunamis. So what we can use is the shallow water equation to model the long period tsunami waves. Now in the picture, what you see is basically the tsunami when it hits the coast. So these are then the shore break waves. Basically when they hit the shore, they keep breaking. And that's not what the shallow water equation is modeling. So these waves, when they hit the shore and start breaking, that's not governed by the shallow water equation. But the shallow water equation gives us the wave when it's still out in the ocean. And the wave height is then small compared to the depth. But then here, when it comes to the shore, then the wave height is large compared to the depth of the ocean floor. So that's not what the shallow water equation would model. For us, it's modeling basically the propagation in the ocean. But then when it comes to the shore, there would be a different set of equations that you would need to model. Especially in this case, when it starts breaking, that's a non-linear wave behavior. And that's not a topic here for today. But the shallow water equation is a very common used equation. And I don't know if you know what storm surges are. Have you ever heard of a storm surge? Not yet. So basically when the storm, a low depression system hits the coast, it not only generates high waves because of the wind speeds, which generate these large swells, but it's also because of the low pressure system moving closer to the shore. You have then less force that pushes the ocean down, which means the ocean basically, the sea level increases due to that low pressure system. And that's called the storm surge. So it's not only the waves which hit the shore, which are large due to the wind, but it's also the sea level rise basically due to that low pressure system you have above. And so when such a storm hits the coast, it has these two effects which worsen the effect. Basically, it's the sea level rise plus then the wave, which the wave heights basically, which both together makes it even more devastating when you have these large systems hitting the coast. So this is called the storm surge, basically, when you have the sea level rise due to a low pressure system that moves in. And that you can model with the shallow water equation. Another equation another example of the application of the shallow water equation is, for example, when you have a dam break. So whenever your water height is small compared to the extent, then you can apply the shallow water equation. And so you can use the shallow water equation to basically model how then the water, the fluid part would propagate inwards into land. It's often it's the nonlinear shallow water equation that is used for that. For us, for this class, what we will attack is the linearized shallow water equation. So it's not quite applicable to for these dam breaks when you want to model that. What you also use is the shallow water equation in atmospheric science. And for atmospheric science, you can, for example, model these dust storms, these flows, basically, these storm fronts, how they propagate. Something you can use the shallow water equation to model. So here you have a dust storm. It's probably in Jeddah. A big front that hits the city. And then when we go to different planets, what you see, for example, on, you can take Jupiter or Saturn, what you have these atmospheric features, these turbulences. And these systems you can also model with the shallow water equation. So it's anything that is like dealing with fluid or fluid dynamics, like air or water, and where the depth is shallow compared to the extent, the area, you can apply the shallow water equation. So what I want to do today in the class is basically quickly show you how this shallow water equation can be derived from the conservation laws that we looked at. How you would end up with the, in our case, the linearized shallow water equation. And then we want to use higher order finite difference schemes, stencils, to solve then that numerical. Is it clear? Good so far? Good, then let me finish here the slides. This slide I can show you when we come to the implementation then of the shallow water equation. So let me quickly show you first how to derive that equation that we see here. For that, I use the whiteboard here again. If you want, you can take a pencil and a paper, right? Or you just look at the notes that I put down, and I'll send you the notes as PDFs anyway. Good, let's try that. Let's connect here. Good. So now you should see the notes, and what we start with is the shallow water equation. So let's start with that first. Maybe use a different color here. Good. So what we want to start with the shallow water equation. And then in the second part, we come to the higher order schemes. So what we start with is basically with the two conservation laws that are important to model these fluid phenomena that we just looked at. And so one is the conservation of mass. The other one is the conservation of linear momentum. So let's recall quickly these two conservation laws. So let's recall the conservation laws. For mass and linear momentum. So we had the time derivative of rho plus the divergence of rho times v, velocity field equal to 0. So that's the continuity equation. That's conservation of mass. What we saw before in the lectures. And now let's look at linear momentum. So let's use the material derivative, dt, of the velocity minus the divergence of the stress is equal to the body forces. That's linear momentum. So when we look at the shallow water equation, the forces here are forces due to gravity. So what we consider as a volume force due to gravity. So that drives the tsunami waves. You can write it such that we have the force is equal to rho times g, the acceleration, times h. H is then being the water depth. Now, we have to make two assumptions. One assumption is basically that we're dealing with an incompressible fluid. And so the flow field V, velocity field, the divergence of it vanishes. That means it's incompressible. So let's use these two assumptions. One is that the fluid is incompressible. And that we can write as the divergence of the velocity field is equal to 0. Or if you like, it's equivalent that the material derivative of rho vanishes. It's something we also saw when we looked at the conservation of mass before. So that means the fluid is incompressible. And the second one is we look at a specific type of fluid, so-called a Newtonian fluid. And so a Newtonian fluid can be written where the stress is a sum of a stress which is a hydrostatic pressure stress plus a stress which is due to the viscosity of the fluid. So the hydrostatic stress, we can write it as P is the pressure and I is the unit tensor, if you want, because it acts in all directions isotropically. And plus this fluid stress, so we denote it as TF. So P here, that's the pressure. If you want, is the hydrostatic pressure. And so the I this thing here, that's just a unit matrix or unit tensor if you want, with ones on the diagonals. And then TF, that's now the Newtonian fluid is a stress, fluid stress if you want. Which is due to the viscosity of the fluid. If we can write the stress in such a way that it's the sum of a hydrostatic pressure stress plus a fluid stress, then this is called the Newtonian fluid. So fluids like water or air, like under normal conditions, they are close to this idealized fluid, to these Newtonian fluids. So for example, water or air under normal conditions they are close to these idealized Newtonian fluids. If you want, as a counterexample, for example, you can take paint, which is like non-wet paint. That's a non-Newtonian fluid. If you want blood, is also non-Newtonian. Or if you want, often polymer solutions are non-Newtonian fluids. So if you want non-Newtonian, that could be paint, blood, or polymer solutions. So let's come back to our assumptions. So with these two assumptions, that fluid is incompressible and Newtonian fluids, what we find are the so-called Navier-Stokes equations, which are like the main equations in fluid dynamics. So we find the Navier-Stokes equations, which is first, that's the incompressibility condition equal to 0. Let me quickly get rid of these notes here. And now the second equation becomes the time derivative of rho times velocity plus the divergence of rho times is tensor product V times V equal to minus grad of pressure plus rho G acceleration plus what we have here is the divergence of this fluid stress. So these are the incompressible Navier-Stokes equations, if you want. So using conservation of mass and linear momentum leads us to these Navier-Stokes equations. Good, and they are now the root equation basically when we go to the shallow water equation. So let's look at tsunamis. Tsunami waves. So if we look at tsunami waves, what we see is that we have wave on top with the long wavelength. And then we have like a, let's say a mean ocean depth here. We can call that H. And then what we want to model is basically these small perturbations due to the sea level. Okay. We can call these the P. It's the wave height basically. In 2D depends on X and Y. So if you want the wavelength here has to be long compared to the depth now, to the ocean depth. So assuming that we have a long wavelength, and neglect the vertical acceleration, so we find the shallow water equation. Which can write as this second order time derivative of this height P is then equal to the divergence of let's use V square grad of P. With P is the tsunami height of tsunami. And V is the wave speed basically, which is a function of G times H. That's the tsunami wave speed. H here, that's the ocean depth. So when we want to model tsunami waves, that's the shallow water equation that we can solve. And then we have the height of the tsunami when it's still out in the ocean. The long wavelength approximation, what you can, if you want, if you would take the ratio between the ocean depth compared to the wavelength, the tsunami wave, that should be smaller than 1. That's then the assumption that we have a long wavelength. Compared to the ocean depth. So that's when we are in this regime for the shallow water equation. Good. And so if you want to model tsunami waves, that's the equation that we can use. It's a linearized shallow water equation. But you also see if the depth of the ocean is deeper, the wave speed is higher. And if the ocean becomes shallower, the wave speed becomes slower, so the tsunami wave will slow down. Good. So that's the first part. Now we see how the shallow water equation derives from these two conservation laws, mass and linear momentum, which lead to the Navier-Stokes equation. And if we further simplified for a long wavelength wave, then we end up with the shallow water equation. Good so far? Any questions? Good, then what we do now is basically we look at higher order finite difference schemes in order to solve that. So we had first and second order schemes. Now let's look at the fourth order scheme. So let's start with higher order finite difference schemes. So let's come back to the finite difference method. And in this case at a higher order schemes. So what we aim for is a fourth order scheme, for example. So let's see how we could create such a scheme. And let's start again with the approximations that we know already. So we had, for example, the derivative of function f of x, which you can write as the limit when a small increment h goes to 0 of fx plus h minus f of x divided by h, which we can approximate now, for example, by fx plus h minus fx by h plus the truncation error, which is O of h when we use a forward difference scheme. Then we had the backward difference scheme, so we would approximate this with fx minus x minus h divided by h. And again, it's a first order scheme. Truncation error is linearly related to the increment h. This is the backward scheme. And we also had a centered scheme, so let's write that down. So we had fx plus h minus fx minus h divided by 2h. And this is now a second order scheme, so the truncation error behaves with h squared. This is centered. Good. what is often done when we look at these finite difference methods, it's defining the stencil, the finite difference stencil. So let's quickly look at that finite difference stencil. So in this case, for example, we want to evaluate at this center point. That's our value, let's say at position xj. And so when we use these schemes above, basically we have to look at its neighbor points, either at -h or +h. With these increments, this grid increments, if you want, small h. So for these approximation, we use small differences. H is delta x. So if you want the stencil, for example, of these, the forward scheme. So if you take the forward scheme, you have f of x and f of x plus h. So that would be your stencil for the forward scheme. Similar for the backward scheme, or if you want the centered scheme, that would take the two neighbor points basically. So that's called the finite difference stencil. So the question is basically now, how do we achieve a fourth order stencil or fourth order accuracy for that derivative? So let's quickly put down that question. Can we ask for a fourth order accuracy? So let's just try, and let's try what we can do when we take intermediate steps, for example. Let's see with intermediate steps. That we have du dx, our function derivative. If we do so, then what we can look at is a scheme that has a coefficient a times, now let's use an intermediate step of 3/2 of h minus f of x minus 3/2. So that would be like a centered scheme with an intermediate step of 3/2 h. And then we combine it with a second scheme centered, but only with 1/2 of h. Good. So can we find these two coefficients a and b to have a fourth order accuracy when we combine these intermediate step evaluations? Like adding a centered scheme with 3/2 of h and adding a centered scheme with 1/2 of h. Now the question is, what do we need for A and B to be in order to achieve a fourth order scheme? And that's basically an optimization problem. You try and find these two coefficients A and B such that it becomes a fourth order accurate scheme. And actually we do find a solution in this case. So what we find is for A, is this value of 1/24. B is for 9/8. It's basically an optimization problem you can think of. So with these two coefficients, A and B, so we do achieve a fourth order accuracy now. So let's look at the finite difference tensor for this fourth order scheme. So we have our midpoint where we want to evaluate the derivative. And then we had these two neighbor points at plus and minus h, but what we now do is basically we evaluate at these intermediate steps. So it's -3/2 of h, -1/2 of h, etc. And so you see for the fourth order scheme, we need these 4 different neighbor points to evaluate the position at xj. So the observation I want you to come to is basically when we increase the order, the stencil becomes wider. So for fourth order accuracy, the stencil becomes bigger or wider. It's kind of an obvious observation, but when we come to the pseudospectral method, what we will do is basically we increase the stencil as much as possible. So we make it as wide as possible to achieve then the highest possible accuracy as well. But so for net, yeah?
What do you mean by bigger? It means that more dots included, or the edge is bigger?
No, we include more information from more neighbors.
Like more, like here is 4 number, right?
Yes. So
So
here you have these 4 neighbor informations that you include for your stencil. And then you achieve a fourth order accuracy.
okay.
Above we had 2 neighbors and we achieve second order. If you only take 1 neighbor, you achieve a linear order, first order scheme.
Okay.
And so you see where it goes basically. If you want to have a 6th order scheme, in order to achieve that accuracy, what you would need is some additional neighboring points. And so the stencil becomes wider or bigger and bigger if you want to increase the order of the scheme. Good, so I gave you an example of a fourth order scheme, but how could you, let's say, just create a different fourth order scheme? And in order to find such schemes, what is very convenient is to write down the Taylor series again. And then see if you can combine the Taylor series such that you achieve higher order approximations. So let me quickly put that down. So let's recall the Taylor expansion, the Taylor series. So let's be a bit tedious and write it down to higher order terms. So we have f of x and first derivative f prime of x, second derivative 2 prime of x. And then let's keep going. Third order derivative, fourth order derivative, fifth order derivative, and then let's stop here. Then the rest is sixth order. If we truncate here. So this thing here should be 5. So Roman 5. Okay, and you saw from last time when we did this, we also write the expansion for f of x minus delta x. So let's quickly do that. All that we have to consider is basically just these sign changes. Fourth order and fifth order, again with the minus term. And the truncation error is again sixth order. Good, from this we can now find the expression, a higher order expression for the second derivative with the truncation error of fourth order. Now, instead of me doing it, you can take a piece of paper and then do this for your homework. So let this be a part of your homework then. And you want to have a fourth order scheme for the second derivative, x. Then how would you combine these two Taylor expansions in order to have a truncation error of fourth order? It's a bit tedious to write down, combine, but there's no magic in that. Straightforward. Good, and that's basically all when it comes to higher order schemes I want to give you. We could go on 6th order, 8th order. What you would see is the stencil becomes wider, bigger. And here we would just have more complicated expressions. Which include just more neighbor information, basically. So in seismology, what often is used is a fourth order scheme in space for the spatial derivatives and the second order scheme for the time derivatives. That's a common approach because often in seismology, the time length, for example, of a wave simulation, the time is still considered to be short, but the accuracy of the gradient in the subsurface need to be more accurate. So if we would only use a second order spatial approximation, then we will make a larger error due to more complicated subsurfaces. So that's why often the spatial derivative is higher than the temporal derivative, at least in seismology, but it's often the case. And you saw from the very beginning with these higher high performance systems, they become more efficient when you use higher schemes, higher order schemes. They do like floating point computations rather than retrieving memory. Because the bandwidth, memory bandwidth is smaller than the peak performance that these nodes have. So which favors now usually higher order schemes. So became more and more popular to increase the order of the schemes, to just run them a bit more efficient on the newest HPC system. But again, very often, like in seismology, for example, you have second order and fourth order schemes that you use. Good. Any question to that?
I have a question.
Mm-hmm.
You want to put this, for example, in Python or, well, MATLAB. You can just change h by 2 delta x, for example, and that will work. I mean, you just, for example, in Python, you have the array, and you need to go one step forward and backward. But if you put 3.5 here, you can get confused because you said, well, it's 1.5 forward and behind, but in a rate that doesn't exist, right?
Right, so intermediate steps, that's called a staggered grid scheme, a staggered scheme. Staggered schemes, they have become very popular in seismology. And one of the main advocate of staggered schemes for finite difference schemes for seismology has been Jerry Schuster, for example. Jerry has, together with a student or postdoc, a paper out in 1990. It was called the parsimonious staggered grid finite differences for the wave equation. And that has become a very popular approach. There's also work done by Jean Virieux on staggered grids. And they show that for the wave equation in particular, these staggered schemes, they adapt very well to the wave equation. So what you have here with these intermediate steps is called a staggered scheme. There's a bit, you have to wrap your head around it in order to implement it. What you can do with the Taylor expansion here below, you can also find fourth order schemes without these staggered steps. And that's what you will do basically for the homework. So it's up to you if you want a staggered scheme or not. So in our case with the tsunami waves, it's fine to go without, but the staggered schemes have particularly become very powerful for wave propagations. One reason is basically that you want to evaluate the velocity and the stress at slightly different positions. I can quickly draw you such a scheme. For example, when you look at the grid, let's see, these are our points where we have velocity. Let's say we define velocities on these points. Now a staggered grid uses these intermediate steps, for example. And so what you can do now at these intermediate steps, you would evaluate the stress T. For example, Cherry, he showed that this becomes more accurate when you do it this way in such a staggered scheme. So if you want a staggered scheme, use intermediate steps, and if you want a very simple one, is this plus 1/2 minus f of x minus 1/2 divided by h. This is second order. And then again, you can increase the stencil, like what we did above for fourth order, for example. And if you want, you look at the paper from Luo and Schuster. That came out 1990. It's called Parsimonious Staggered Grid. Finite differencing. the wave equation. That appeared in GRL journal. Simple. It's one of the main references for all these staggered schemes that we use now in wave propagation schemes. There's also from Jean Virieux, if you want to look him up. He was also advocating these staggered grade solutions. So for this class, we don't really go further into these staggered schemes. What we'll implement is a non-staggered scheme, where you just evaluate it at these full increments. Use the neighboring points. So very simple, you derive it here with the Taylor expansions. And then you find a fourth order scheme, for example, for the second order derivative. Maybe as a quick note on resolution, grid dispersion, and grid anisotropy. Just a note I want to give you, just to be aware of, if you have a grid we saw it already a bit when we did the stability analysis. Now, dispersion means, or grid dispersion means that the wave speed becomes a function, of the wave vector. Okay, so the speed of the wave can be different if it travels in one direction compared to traveling in another direction. This effect is called grid dispersion or grid anisotropy. And any discretization has that effect. So as soon as we start discretizing the wave equation, use a grid to solve it numerically, we will have grid dispersion. We will have an anisotropy effect. That waves in one direction might travel slightly at a slightly different speed than in another direction. So this usually has to be analyzed when we implement numerically the wave propagation, for example. And this will be analyzed numerically to see how strong the effect is. Just to be aware that any scheme that we will look at in this class has that effect, has a grid dispersion effect. Obviously, you want to minimize that effect, for example. The grid shouldn't introduce you an additional anisotropy or an additional dispersion effect. So it's usually part of the numerical analysis. Good. So by that, we would basically come to the homework, the new homework, the tsunami waves. Is that okay? So let me stop here. Quickly show you again the slide. So let's come back to the shallow water equation, and that's the equation on top you see, which we want to implement now with a higher order scheme, a fourth order scheme. So think of the time derivative needs second order. There we can just leave at second order. But now the spatial derivatives, we want to have a fourth order scheme for the spatial derivatives. So let's look at the homework. So the homework here, which we can start this week, and then we can look at it on Thursday again. But probably I can just let you work out the homework on Thursday without actually, well, we can quickly meet online on Thursday as well, mostly to discuss the previous homework, and then in case you have questions about this new problem set, can discuss that as well on Thursday. But so the problem set is basically you start with the shallow water equation, and then we can further simplify it a bit, but just assuming that this velocity term is not changing much. So we take it out basically of the derivative. And then we have a very simple shallow water equation that we can implement. Second order time derivative equals to then the second order spatial derivative times the velocity, wave speed squared. It's called the homogeneous equation because there is no source term acting. And now we can obviously play a bit, see how accurate is that assumption that the wave speed is constant compared to actually allowing the wave speed to vary with the ocean depth. So the problem is basically mostly this. First, figure out what's the fourth order scheme in space. And then see how we can compare the homogeneous versus the inhomogeneous wave speed case. And to play around with it, that's the little tsunami code that you will have in this homework folder. And this is a C code now. So start looking a bit at C. And if you figured out these orders, higher order schemes, you can put in the fourth order scheme. So the template already has the second order scheme implemented. Second order in time and space. And your task is basically add the fourth order in space. Okay. How does that look like? I can quickly show you the slides, which you can use as well, which help you already with this homework. Now let me switch to the slides. It's this one here. So if you simplify it into this homogeneous form, you can take out the wave speed from the derivative and you end up with these two spatial derivatives. in X and Y direction. Good, then the question is how to increase the order, the spatial order. And here it's already given you, for example, these fourth order schemes for space. So in your homework, try and derive these schemes on paper to see how you would basically use the Taylor expansions, combine them in order to find these fourth order schemes. It's a little homework exercise. And so that's basically the change of your implementation. Now you have these fourth order schemes which you can implement. If you put this together, what you will see is you end up with a scheme like this, for example, fourth order. And then you can use that for the tsunami code. And the code is set up to propagate tsunami waves out from the Sumatra earthquake. But it's instead of having a more realistic source, it makes just a very simple point source. And then you would see how these waves propagate away from that point. But it includes the bathymetry, a realistic bathymetry, and then you see how the waves would react to that bathymetry. So that's what the example is. You have here a low resolution image of the bathymetry.
Professor,
Yeah?
we cannot see the slide, I think. Or just I.
Yeah, the tsunami title.
The tsunami, yeah.
Which one you don't see?
I just see tsunami slide, no figure. Yep, I know, I see. Okay.
This one you see?
I don't see this before.
Now, yes.
If I put it full screen, you still see it or not?
Yep, I see now.
And now?
Yes.
The same slide.
Okay. So again, the point source is already implemented. Basically, it just distributes a point source onto a few grid points. And then we have Dirichlet boundary conditions, where we just set the displacement or the wave height to 0, the boundaries. And the seafloor, the ocean depth, that's basically read from these bathymetry data set that you also have in that homework. So it reads in the bathymetry and then it has the seafloor height. So that's the discretization, how we would discretize it, this domain. And then you can basically solve the tsunami waves. So the code should already run when you use just the implemented second order scheme. You can quickly test if that's the case, if it runs through. And then you add basically your fourth order scheme. And it outputs you these the wave heights every 100 time steps. And there's a little MATLAB script in order to plot these. So you should see then how the waves propagate out.
Sorry, yeah. Okay. This presentation is on the GitHub.
It's in the homework folder as well, yes.
Okay, thanks.
So it's part of the material, the homework material. I can quickly show you maybe how the code would look like. So can you see here the code file? Not sure if you can read it, it's quite small. But this is basically this little C code. It's the template. which already is set up such that it should basically run for second order. So it's setting up the grid, it reads in the bathymetry, and then runs this main program here. And there is not much for you to change in that respect. Here, this is the source, the boundary, but you see this part here. That's where you would add your modifications now. So it has the second order above, that's already implemented. All you would do is basically now add a fourth order scheme. And then play around with the homogeneous wave speed and the inhomogeneous wave speeds. See how the implementation would change when you allow for an inhomogeneous wave speed. So again, there's not much for you to code. It's basically only here a little bit C that you can add to this program. And then you should see what the differences are between second order accuracy and fourth order accuracy already. Good so far? Good, so you have all these in the homework folder 3, which I will upload or just have uploaded, I think already. So you just git pull it, and then you can already keep working on that one. Try finish the homework 2 by Thursday. So let's see, finish it by Wednesday, and then we can discuss it on Thursday. And if you want, already look into this part, and then we can also discuss it on Thursday. But this one would then be up to Thursday next week. Good.
Sorry, sir.
Yeah?
So is our next class on Thursday?
Yes.
Okay. I just remember it's on Wednesday, so I'm...
No, we shifted Wednesday to Sunday, to today. Thursday stays, but Thursday 3 p.m. again.
Okay, got it. Thank you, Professor.
So now 3 p.m., Sunday and Thursday. Good. And if there are no more questions, then I wish you happy coding. Code away your examples. And have fun with the wave propagation. Kind of fun when you start plotting the images and you see how these waves propagate. That's a nice quick feedback when you get it right. Yeah. Good. Then I would say let's meet again Thursday. Next Thursday, we'll quickly discuss homework 2, homework 3 if you have questions already. But we can keep it short on Thursday, I would say. Good? Good, then I wish you good Sunday.
Thanks.
Enjoy your time. And see you on Thursday.
Okay, bye.
Good, everyone. Bye, everyone.
Bye, Professor. Bye, everyone.
Bye, thanks.
Bye.